Thanks everyone so much for coming. Well, we'll make a start. It's amazing what the weather can do and how much it impacts us all at different times. Smoke haze this morning, storms rolling through, dusty now. And unfortunately, the storms are not enough today to do too much for the fires, and they've probably started more, unfortunately. So, I'll just start with a really quick, welcome to the Bureau. So my name's Nick Logan. I'm the State Manager of New South Wales. Just for the short period this week, just filling in for some leave relief. I'll just start with just a quick acknowledgement of country. So before commencing this meeting, I just wish to acknowledge the traditional custodians of the land on which we are meeting here today, and pay respect to the elders, both past, present, and emerging, of the people of the Aurora Nation and the Gadigal tribe of Sydney. And yeah, it's a great turnout, and so it's really interesting for me to hang around and listen to a few presentations, and welcome to everyone, and I hope it's a really interesting evening. I'll hand back over to Andrew to continue on.
Yeah. Thanks, Michael. I won't take too much time, but this is an Engineers Australia Water Panel meeting. Thanks everybody for coming along and for your patience. We've got really exciting talk, and great to have Tess up from Tasmania and Anthony from Newcastle. So thank you so much for coming up and speaking to us. Really topical talk. So without further ado, over to Anthony, please. So thanks everyone for coming, and sorry we're late, but out of our control. We did the best we could. I'm going to talk today. We're going to interchange. I'll start off and sort of give a bit of background about what we're doing and what the problem is, and then Tess will come and talk a bit more about these mysterious paleoclimate records and how we possibly get information from ice cores in Antarctica and how it can be useful for telling us about droughts in eastern Australia, and then we'll finish off with some of the implications and some of the ongoing work that we're doing to try to make the best use of this science that's emerged over the last 5 to 10 years. So what's the problem? So we're engineers here, so all familiar with the IOD assumption, this assumption that extreme events are independent and identically distributed. So this is taught, hammered into us as engineers, and basically all the infrastructure planning, design, and so on is based on this IOD assumption, which is also referred to as the stationary climate assumption. So the assumption there is that the chance of an extreme event today is represented by the chance of the extreme events that we see in some observational record, and that chance of that extreme event will stay similar into the future for the lifetime of whatever piece of infrastructure it is that you're dealing with. But there's been a few problems identified with that stationary climate assumption or the IOD assumption. And so just a couple of the key ones are, and particularly related to this talk with the paleoclimate work, is that the instrumental record is not long enough to capture the full range of historic variability. This is particularly the case for somewhere like Australia, where we have really large interannual to multidecadal variability, but that combined with the fact that the instrumental records are about 100 years at best for rainfall, and even shorter for streamflow, 50, 60 years if you're lucky. And in a lot of cases they're a lot shorter than that. So because of these short records and that they don't capture this full range of variability, even if we think we know what the worst on record is, and even if we design or build infrastructure to deal with the worst on record, it may not actually be the worst that's occurred. So the climate, there was a lot of things that happened in the climate before the records started to be collected. So by records I mean the observations, station-based observations. The other thing as well with the impacts of anthropogenic climate change and so on, this stationary climate assumption sort of falls over when you want to look forward into the future, because your assumption is there that the instrumental record is also representative of what might happen in the future. Now, there's at least two reasons why the future might not look like what the instrumental record looks like. And one is, as I said, anthropogenic climate change, but the other one is a lot of the stuff we're seeing in the paleoclimate records, which we'll go into a bit more detail later, pretty clearly show that what we see in that instrumental period is or put it this way, what we see in the pre-instrumental period is a lot different to what we see in the instrumental period. So that's the second problem. The third issue is IOD assumption, stationary climate assumption. It's a statistical, empirical calculation. It doesn't really take into account the physical mechanisms which actually deliver the extremes to places, to Australia. And so Australia, we know, it's an island continent. We're surrounded by 3 major oceans and the atmosphere. And there's all sorts of interactions that are going on between those oceans and atmosphere that are delivering weather events to different parts of Australia at different times, at different scales of temporal and spatial variability. None of these physical mechanisms are actually taken into account in that stationary climate assumption. We're just taking the observed record, calculating some statistics from that, without actually giving much thought to the physical mechanisms that cause those statistics. So this is just an example of some of the processes which affect Australia. So there's ENSA there, Indian Ocean Dipole, SAM, all these other ones. But the one I want to focus on today is the interdecadal Pacific Oscillation, because today we want to focus on droughts, and the droughts that really worry us are the really persistent, long-lasting droughts, so 5 years plus, 10 years plus. So these are the things that are associated with multidecadal variability, so 20, 30-year scale variability, and a lot of this has been linked to this interdecadal Pacific Oscillation. So that's what we focus on. It's not the be-all and end-all, but it is the focus for today. And so this is just a couple of different versions of the IPO over that period where we have instrumental data. So the last 120 or so years, this is based on sea surface temperature measurements. And it's similar to El Nino Southern Oscillation, where El Nino Southern Oscillation is warming and cooling of the tropical Pacific on a cycle of 2 to 5 years. The interdecadal Pacific Oscillation is warming and cooling of the whole of the Pacific, but it's on a scale of 20 to 30 years, a cycle of 20 to 30 years. So that's the difference. But it's all about the index is measuring sea surface temperatures in the Pacific, and what that's picking up is some of those oceanic cycles that I was talking about, which interact with the atmosphere, which deliver the weather events to Australia. So what we know from this instrumental record is that when we're in an IPO positive phase, so since about 1980, when we're in an IPO positive phase, La Nina events are far less likely. So La Nina events for Eastern Australia bring floods and wetter than average conditions. So if you're in an IPO positive phase and you get a lack of La Nina events, the likelihood of drought is increased, and the length of drought is increased as well. The flip side is when you're in an IPO negative phase, so from about 1945 to the mid to late 1970s, the chance of a La Nina event is elevated, and more importantly, the chance of back-to-back wet years or several wet years in a decade is significantly elevated. And so the chance of a drought is far less likely when you're in an IPO negative phase, and especially the chance of a mega drought, like a 5-year or 10-year plus drought. You can still get dry years when it's IPO negative, but these serious droughts don't really occur in that IPO negative phase. That's what we know. That's what we know from the work from about 20 years ago from Scott Power at the Bureau and these sort of people. What's that got to do with engineering? So the reason why that's relevant to engineering is because, as I said, the typical process for assessing or dealing with climate risk in an engineering setting is you use the empirical methods. Like I said, you go and get the longest observed record of rainfall or streamflow or whatever it is you can find. As I said, about 100 years of rainfall in Australia is the max, 50, 60 years for streamflow. You get that longest observed record and you calculate your key statistics from it, your mean, your standard deviation, your sequencing, your persistence and whatnot. Then if you want to account for uncertainty, or if you want to sample from the extreme ends of the distribution, you do some stochastic modelling to generate thousands and thousands of different replicates or different variations of that instrumental record. But the fundamental point there is it's still based on the statistics that have been derived from the instrumental record. So again, you're making the assumption that the instrumental record is capturing everything you need to capture. And then, once you've got all that stochastic modelling, you then hope you apply that and you calculate your average return intervals and your annual exceedance probabilities and all your design curves and so on, and you hope that that stochastic modelling or that calculation that you've done based on that instrumental record does give you a realistic insight into the true probabilities and risks. So the numbers that come out of that process, the chance of a drought, or what's your 1 in 100-year drought, or your 1 in 1,000-year drought, you're basically hoping that the instrumental record is capturing everything you need to capture. And then you go forward and everything is based on that. That's what happens. But we know that that stationary climate assumption is flawed for the reasons I mentioned before. And there's been work done previously just based on what we know about the instrumental version of the IPO, and illustrating that these drought-dominated and flood-dominated epochs are very strongly linked to this IPO, and again very clearly demonstrate that the climate is not stationary, and that the chance of a drought occurring changes depending on what phase of IPO you're in. And so that 100-year instrumental record is not really a good indication of the true risk of drought or flood. We know this just from instrumental record. So an example I give is a case study that we did up in Newcastle. So what this plot shows here is the probability of a critical event in the Grahamstown Reservoir. So the Grahamstown Reservoir is the main water supply for the Newcastle-Hunter region, and a critical event is defined as when the available water in the reservoir is less than 30%. And so what you can see here is, and again this is instrumental record only, no modelling, this is just based on what we know from the observed record. When the IPO is negative, the chance of a critical event is really low, almost negligible. But when it's in an IPO positive, the chance of a critical event is 20 times greater. All right? And so if we use the whole instrumental record, we think the chance of a critical event is around there, but if we're in an extended IPO positive period, we're way up here. And so again, this just illustrates that if you just base everything on the instrumental record and you don't take into account the physical mechanisms that cause droughts, particularly the long-lasting droughts, you're going to misrepresent the probabilities and the risks and so on of different types of drought. So this raises some interesting questions that did at the time, and those questions, a lot of them still remain. We're still wrestling with those questions. And so some key ones which we'll talk about today is the variability that we see over that 50 to 100 year instrumental record, is that representative of the true range of variability in the system? The other question is, we've got 100 years, we've got a snapshot, we've got a 100-year snapshot of what our climate looks like. Is that 50 to 100-year snapshot, where does that fit in the context of the pre-instrumental history? Is it at the wet end? Is it at the dry end? Is it somewhere in the middle? The other point as well is, what if what the instrumental record suggests is rare is actually a lot more common than we think? And what if what it suggests is extreme is actually quite moderate, and there's extremes that are far worse that happen outside that instrumental period? And then that leads to this question, which as engineers we'll think about. Just because at the moment we plan for the worst on record and we do what we can to deal with that worst on record, but what if planning for the worst flood or drought on record is not enough? What if it just puts us into this false sense of security that we've dealt with everything that the instrumental record says is possible, and even stochastic stochastic modelling to stretch the extremes even further? What if, even with dealing that, it's not enough? It raises some pretty fundamental questions about how we manage water and build infrastructure and so on. And so that was work that we did about 10 or more years ago. And so then it was all interesting, and we had those questions, and then I got a phone call from Tessa Vance, from working for Antarctica CRC at the time, UTAS, and she said, "Hey, I saw your papers on the IPO and linking it to flood and drought risk. I noticed you're just using the instrumental record, 100 years. You've got 2 examples of IPO positive and 1 example of IPO negative. What if I was to tell you I could get a 1,000-year reconstruction of the IPO and get you about 15 or 16 samples of IPO positive and 15 or 16 samples of IPO negative?" I said, "Wow, that'd be really interesting. Can you do it? How does it work? Sounds interesting, but how is Antarctic ice cores related to rainfall in Eastern Australia?" And then she told me what she's going to tell you right now.
Thanks, Anthony. Okay, so I'm going to talk about how we might get these kind of hydroclimate records from Antarctic ice cores. And I'm talking about East Antarctica, which is the bit that's pretty much under the Southwest Pacific and the Southern Indian Ocean. So it's a big chunk of Antarctica that Australia lays claim to, and it's also the bit that's closest to us. So just have a look at this image. I think what Anthony said is fairly clear. How could somewhere like this possibly have any relationship to rainfall in Australia? This is actually one of our ice core sites that we went to just a couple of years ago. It's a place called Mount Brown South, and that's pretty much what confronts us when we land in a little fixed-wing aircraft on skis with a few tents and start setting up an ice core. Then a whole lot of other stuff comes in, including an ice core drill and tents to go around the drill, and we start drilling. So a lot goes into choosing these sites. It's a very expensive kind of science to do. The logistics are incredible to think about. The weather is incredible to plan for. So we really have to be very sure about where we're going, that we're going to get the kind of resolution of records that we want, and that they're going to preserve the signals that we're interested in. And Mount Brown South was drilled only recently. It'll probably be a 1,000-year record, and it's specifically targeted to try and get Southern Indian Ocean records that are relevant to Australian climate. So we think this is probably the first time that someone's drilled a record specifically to get regional climate records for a country, basically. So how do ice cores record climate signals? The major ice caps of the world, Greenland and Antarctica, are basically composed of snow that's been buried over time, turned into ice, and is in layers that go down with depth and time. So at the very surface on the ice sheets, you'll have snow, unconsolidated snow. It's usually actually only a few centimetres. And then we get to this layer called the firn, which is a Greenlandic term that just means consolidated snow, basically. That usually goes for some tens of metres, 30 or 40 metres. And then the weight of the firn above those layers gets to a point called the bubble close-off, which is where the firn gets compressed to the density of ice, and you end up closing off the bubbles that are in the ice and preserving the gas records. All of the other records that we're interested in, that I'll explain in a minute, are preserved right up to the surface. So it's only the gas records that we have to wait till they're buried and closed off to get to those ones. So what happens is that we drill down through the ice sheet with one of these ice core drills. This is an intermediate length drill, so it can do up to about 500 or 600 metres. We also have short drills that do 100 or so metres, and then there's really long ones that can do 2 or 3 kilometres, and they're usually in a shed built around them, and that's a few seasons of work. So from the surface down, we can take home these ice cores to our laboratories. We basically cut them up into different samples, sample them at a particular resolution. For instance, this core's been sampled at 3 centimetres, and then we measure those samples, and each sample is locked to the depth that it came from. The drill very carefully registers the depth each time it does a drill run to get a core. And then we can measure these samples, and we get, from the chemistry and the isotopes in the ice, we get these seasonal cycles. And if it's a high-resolution ice core site like Mount Brown or Lourdone that I'll speak about as well, you can see these annual cycles. Something like water isotopes, which represent temperature, will peak in summer and they're low in winter. Sea salts, which represent storminess across the Southern Ocean, will peak in winter and they're low in summer. So we have multiple different tools that we use to date the ice cores. So once we've got that layer counted dating scale, we register that to the depth, and then we have a record. We have a chronological record through time. And we can start to compare the records to instrumental time series to see what they represent. So there's 3 archives in an ice core. The first one is the trap there that has to get compressed to the point where you can measure it. This is the only way you can measure carbon dioxide, historical carbon dioxide, with true fidelity, because you actually are measuring the carbon dioxide that was preserved in those ice core records over time. We can look at the trace impurities in the water that we melt from the ice. That's things like sea salts, volcanic sulfate, biogenic sulfate, and a range of other things. In one of the cores we've got someone measured lead isotopes and could identify where Broken Hill started smelting. So that just gives you an idea that there is a link between Antarctica and Australia. The third thing is the water isotopes. So water isotopes, the ratio of heavy to lighter oxygen atoms changes depending on where the water was sourced from and and the temperature at which the snow is deposited. So the oxygen 18 isotope that is the one we use to give us site temperature. So that's a very, it's used as a climate scale, but its primary purpose in high resolution isotopes like this is as a dating scale. It gives us that really good summer peak. I think I've explained most of that. So there's various other things we can measure. Dust is an important one. You can look at West Antarctic cores can give you a good record of aridity in Patagonia and Central South America. Cosmogenic beryllium-10 gives you a record of solar cycles, which is great for proving that it's not solar cycles changing the climate currently, because they haven't changed as much as people would like to think. And this basically, when you relate these to different instrumental data, you can look at climate forcings and the climate responses that you get from these forcings, like temperature, changes in precipitation, changes in atmospheric circulation, carbon cycles, and even sea ice extent. So this is not about hydrology in Australia, but this is probably the best example of icicle science across the world. This is from the Epicodome C record, which is in central Antarctica. It was a big European international effort. And you may have seen a figure just like this on an Al Gore presentation or an Al Gore movie. This is the one he was talking about where CO2 gets to in the modern era. So the Antarctic temperature is from measuring the water isotopes in the Dome C ice core, and the CO2 is the actual gas measurements from the same depth registration. And what you can see if you join those together is that they're very closely locked in time. The more important thing, of course, is that they vary over this period between glacial periods or ice ages and interglacials, like the period we're in now. The range is about 180 to 280 parts per million. And that's why paleoclimatologists and other climate scientists are so worried about our current climate, because we're well outside the bounds of anything we've seen for the last 800,000 years. Okay, so now I'm going to talk about the Lower Dome ice core, which is where we've derived these IPO reconstructions from. So Lower Dome's quite a different record to the one I just showed you, the Dome C record. Dome C is in central Antarctica. It's basically a desert. The snowfall's about 3 centimetres a year, so very, very small amount of snow accumulation a year. Lower Dome, on the other hand, gets on average 1.6 metres of snow a year, and sometimes we've seen in some years, 2001 was 3.5 metres of snow. So it's basically the rainforest of the desert. So the reason why you would go to a place like Lower Dome is because you can't get the length of record, but you can get so much more detail. You can chop those ice cores into these small pieces and get multiple 10 to 30 samples a year, which means you get a high resolution record. You can start to look at seasonal scale processes. So Lower Dome's a long record, but because of where it's situated and the way it flows into the various glaciers around it, the top 800 metres of that 1,200 metres cover only the last 2,500 years. So it's an incredibly detailed record, and that high central resolution goes back right through that period. The climate signals from this record are dominated by the Southwest Pacific and Southern Indian Ocean, and if you look at the Southern Hemisphere in context from what's driving a lot of climate in the Southern Hemisphere, you can see that that's not so hard to understand. I've put a dot indicating Lower Dome here, and this is just a standard synoptic map of the Southern Hemisphere. There's a big blocking high type system here. We've got a huge low coming through here. It's already impacting the Lower Dome region, and it's probably going to sweep through and clip across the bottom of Australia. So even on the synoptic scale, we've got that link between Antarctica and Australia. It's really not that far away. It's about 3,000 kilometres from here to here. So there's been myriad studies linking Antarctica and the Southern Ocean to Pacific variability. The Southern Ocean is recognised as one of the primary drivers of global climate, but equally the Pacific Ocean obviously is one of the big drivers as well. And there's strong links between tropical Pacific variability and climate in Antarctica. So ice core analysis from Antarctic ice cores can actually have a look at these kind of Pacific records of Pacific variability. And some early work from the Lower Dome records did link Lower Dome to the mid-latitudes and subtropical latitudes in the southwest Pacific Indian Ocean. So we already had a hint that there was something there that might be able to record record climate relevant to Australia. It wasn't just recording those really high latitude winds or local climate. So the chemical and physical boundaries in the ice that I was describing earlier, the amount of snowfall a year, the chemistry records are the kind of things that we can develop into records that are useful for looking at regional climate. So one of them is the snowfall accumulation rate per year. So that's purely measuring between these year boundaries that we can measure in the chemistry and calculating how much snow fell that year. So we take the distance between that record, convert it to what we call ice equivalent, and then you can convert that back to snowfall now. Another thing is the sea salt aerosol concentrations. So sea salt aerosols are a measure of wind speed over the ocean. They have a fairly short atmospheric lifetime. They're quite heavy, but they're a good record at those high wind speeds of mid-latitude climate variability. The good thing about sea salts is you can measure them in parts per trillion concentration, so you can get really, they're quite variable in the ice core. It's not a linear process. So we can measure them right down to when they're very low, when there's not much going on, and right up to the high concentrations as well. And they're very stable. Some of the things we measure are quite volatile. Some of the sulfate compounds are volatile. They can evaporate from the ice core after you've drilled it. They can move within the layers in the ice core. Sea salts tend to stay where they're deposited, so they're a good record. And at coastal lower elevation ice core sites, they really do represent wind speed across the ocean. So in the higher elevation inland sites, there's a lot of different processes going on. We get this thing called diamond dust, which is clear sky precipitation. That can really confuse sea salt signals and where they're coming from. But at these coastal sites, it's pretty much all just what falls on the ground, gets deposited and stays there. So what we found was that the salt concentrations in the summer period of the ice, so we could narrow the concentrations down to these seasonal signals. They vary with Eastern Australian rainfall. So there's a very quite a strong, surprisingly strong relationship between rainfall across this region and the summer sea salt concentrations. And there's a strong link to the interdecadal Pacific oscillation. So it tends to be that in the positive phase we get this stronger link to the lower latitudes, and that rainfall signal really gets ramped up. So that was part of the reason why Anthony and I started talking and saying, well, we need an IPO reconstruction for two reasons. One, because it's useful, but also because it'll help us to understand the rainfall proxy. We'll be able to tell when we've got more fidelity in the record. So this is the rainfall record that we produced from those summer sea salt concentrations, and you can see that this is the instrumental period. And you can see how much variability there is in the past, and that was what Anthony was talking about. You can't use just the last 100 years to represent what has happened in the past or what could happen in the future. So this is all very interesting, but we did know whether we could reconstruct the IPO, and we also needed to try and figure out what was controlling the IPO signal, because although it's not a local signal at Lower Dome, it's a maritime signal across the mid-latitudes, but it's still not, no one's saying that there's a direct link between something in the Pacific and snow falling at Lower Dome. There has to be something in the southern Indian Ocean, in those mid-latitudes, that's representing the IPO, and that leads to the signals we get. So why is there an IPO signal? So we had a look at decadal wind variation in the southern Indian Ocean using some of the reanalysis packages out there. And what we found was that the winds switched between from a more zonal pattern to a more meridional pattern. And this happened when the transition from a negative to a positive phase occurred. And I've got stars on those because I have to explain them on top. So we use this phase shifting to reconstruct the IPO. We could use a number of different records, but that switch between the sea salt seasons was the really primary one. and it allowed us to identify these drought periods or drought-prone periods in the rainfall. So Anthony said I had to explain zonal and meridional because I was talking to engineers. So the zonal wind is basically the average westerly wind flow in the mid-latitudes. It's the roaring 40s, the furious 50s, the screaming 60s, I think is the other one. The meridional is the north-south energy transport that occurs as part of that storm system. So what we think is that in these IPO positive phases, we've got a slightly more meridional pattern to that westerly flow, and that allows us to get the link to Australian climate. So what we plan on doing next, we have reconstructed the last 1,000 years, but we have the ice and we have the samples to be able to reconstruct for the over the last 2 millennia. So this is just an example of, or this is actually the sample resolution we have over the last 2,000 years, and you can see it. It's very high at the surface where you've got this snow and fern, and then it declines down to here, and then it jumps back up again. This is where we got to a point before my time where they said, we're running out of sample resolution, let's go to 2.5 centimetre sample resolution. So it's literally where they started cutting the samples smaller so that we could get that really high resolution back further in time. So this is hot off the press. This is just the rainfall that we've produced from that extended data. I've only done this in the last few days, so I can't tell you anything about the new statistics from it, I'm afraid. But this is the instrumental period, and this is the dry period that we identified in the 11th century in the 2015 paper, and then our record ended here. So now we've got all of this data, and I'm just waiting for a few last bits of analysis to get this last few years here as well. So you can see that the variability there, it's nothing dramatic changes overall, but there's a hell of a lot going on. And certainly one century is not the same as the next century. So I think I'll hand back to Anthony now to discuss the implications.
Yeah, so in summary, based on the 1,000-year record that was published a couple of years ago, what we find is that this term mega droughts, so droughts greater than 10 years, there's actually a period there in this 1100s that Tessa was talking about where we had six of those mega droughts in a 300-year period. So 6 10-year plus droughts in a 300-year period, including one 39-year drought. So where was it? Yeah. So this century here. So this is this 1100 period. That one there looks like a 39 years of drought conditions. What we understand drought to be from the instrumental record. But more importantly, in that 100-year period, 1100 to 1212, drought conditions about 80% of the time. So that's not saying an 80-year drought. That's saying, a 10 or 15-year drought, then 2 or 3 years of non-drought, then a 20-year drought, then 2 or 3 years of non-drought, then a 30-year drought. So 80% of a century in drought conditions. And it's obvious that we don't see that in instrumental records. So that's if that century could start to occur tomorrow. We don't know. That's something that's possible in the system. So the important point to take home from that is we've had serious droughts, and undoubtedly they were serious, and the one we've got now is serious. We've had 3, this one is the 4th, or some of the people are saying it's still connected to the Millennium Drought. But the important point is that while those droughts definitely are serious, we've had worse before. And we've had droughts like that on a lot more regular occurrence. So 6 in a century compared to 3 or 4, and 80% of the time in drought. So what have we started to do with that information? So what we did, again, we went back and revisited some of the work we did in Grahamstown in Newcastle. And the beauty of the work that Tessa's done is wherever we've got that strong correlation, so basically anywhere here, we can do catchment-specific rainfall reconstructions, or site-specific actually. So station-specific rainfall reconstructions, which is what we did for the Williams River catchment that feeds Grahamstown. And what we did was looked at different statistics, but the ones I want to focus on today, we're talking about drought duration. And so this is just a histogram showing the number of times droughts and wet periods of a certain duration occurred in the instrumental period. And so you see in the Grahamstown area, we've had and one example of a 10-year wet period. We've had one example of an 8-year drought, a 6-year drought, a whole heap of 2 or 3 or 4-year droughts. Now, that's that instrumental period. That's what we understand our climate to be like. That's what we assume represents. That's what we assume represents the variability in the system. But if we go and use that 1,000-year reconstruction, and we repeat that process for the other 9 centuries in the last 1,000 years, just clipping at 1,000 to 1,100, 1,100 to 1,200, what we see is this. Now, you don't need to read the numbers, just look at the shape of the curve, the shape of the histogram. That's the instrumental one that I just showed you. This is 1,000 to 1,100, 1,100 to 1,200, 1,200 to 1,300, etc. The thing that jumps out is none of them look like that. This is the 1,000-year record overall. So if you want to take the 1,000 years, that looks very different to the last 100 years. If we were here and our instrumental record was 1,000 to 1,100, our assumption is that the next century is going to look like that, but it didn't. It looks like this. If we're here, our assumption is it's going to look like that, but it didn't. It looked like this. At no other point in history has the next century looked like the previous century, but yet at the moment, everything that we do assumes that the 2000s is going to look like the 1900s. Based on what? What is that assumption based on? There's not much evidence to support that assumption. And so again, going back to my other point, even if you use this information and the statistics from it to develop stochastic modelling and so on, you see that the underlying statistics change as well. The average doesn't change that much, but the variability changes quite a lot, 10, 12%. The other important thing is the duration. So the maximum duration of a drought jumps from 8 years to 12 years, so 50% increase. On the wet side, it's even worse, 10 years to a 39-year drought. So there's implications for flooding and so on as well, but this talks about drought. So conclusion from that is that the instrumental record misrepresents the mean, the standard deviation, the persistence, the clustering, the sequencing, basically everything that's important. Every statistic that we use to define drought or design solutions to drought is misrepresented by the instrumental period based on what we understand from the paleo records. So we've got 10 examples of a 100-year snapshot, and every single one of them is different, but our assumption is that every single one of them will be the same. But that's all very interesting, but that's just based on one paleo record ice cores. So the next question is, well, why should we trust Tessa and her ice core? Is it real, or is it just some... it's very hard to verify because we're talking about hundreds of years ago. There's no other information. But what we do have, and what's come out in the last 2 years or something in particular, is there's always been paleoclimate information, but Tessa's record was the first high-resolution one. So by high-resolution, mean annual scale or better. So when you get to annual scale, you're starting to get into the scale that's useful for hydrology. Prior to ice cores coming onto the scene, you're talking about sediment paleo records and other things which were of the decadal scale or worse. But now we're getting to the stage where we're getting annual and even seasonal paleoclimate reconstructions. So I just go through a few other lines of evidence which are nothing really to do with us. These are independent records. So a study by Kathy Allen and co in December using tree rings from Tasmania. And so I won't go into the detail of it, but they did a 500-year reconstruction to come up with a drought atlas for Australia and just take you to the key finding. Despite the severity of the Millennium Drought, the 5 worst single years of drought happened before 1900. So pre-instrumental. So again, consistent with the conclusions. So I was involved in this study, but we didn't produce the paleo record. This was based on speleotherms, so cave deposits from the Wombian Caves, just southwest of Sydney, near the Warragamba catchment. So Michelle Howe, PhD student that went through Newcastle, used that information to reconstruct rainfall in some subcatchments in the Murray-Darling Basin. The key finding from that is that if this black line here, this is the instrumental period, so 1880 to 1980, it finishes at 1980 because that's when the Wombian record finished. That's the exceedance probability of your wet periods, and this is the exceedance probability of your dry periods. So what this work found was the chance of a wet period of 10 years or greater length was 10 times more likely if you look at the paleo information than what it is if you just look at the instrumental period. And the same thing for the drought. Right, so a drought of greater duration than 10 years is 10 times, the chance of that happening is 10 times greater if you look at the paleo record compared to if you look at the instrumental record. So that's using cave deposits. So we've got ice cores, tree rings, cave deposits, all saying similar things, that these pre-instrumental period don't look like what we see in the instrumental period. Another one, totally different again. So this is John Chivy and Cameron Barr from Uni of Adelaide using leaves that fell into a lake on Stradbroke Island and consolidated, and then they used that to give a 7,000-year ENSO history. And so what they found was up to about 5,000 to 6,000 years ago, things were dominated by La Nina events, but then about 3,000 years ago, things flipped into an El Nino-dominated phase, so a drought-dominated phase. And so said there's substantial droughts during this period because of the El Nino, drier than the Millennium Drought. But the key conclusion again was the probability of drought worse than a Millennium Drought is much higher than the current prediction of 1 in 10,000 years. We're thinking it's of the order of 10 times more likely. So again, consistent with the cave deposits, that's the sort of order of magnitude that we think these drought risk estimates are out by. Factor of 10. Another one, this one was an IPO reconstruction, so similar to what Tessa and colleagues tried to do, but instead of using ice cores, these guys used tree rings from Vietnam. So something totally about as different as you can get, but encouragingly and interestingly, their IPO reconstruction, we compared the record to Vance et al. And revealed strong agreement, despite the vastly different nature of the sources of the paleo information. So this gives us some confidence that what we're seeing in the ice cores and the IPO reconstruction is real, and that there's some value in it. And so based on that confidence, this gives us reason to extend things back into that 2,000-year period, but it also gives us some concern that what we're seeing in those IPO records is real, and that this 39-year drought is not a furphy, and it possibly could have happened. And so a 39-year drought is floating around somewhere in the system, and so if all the mechanisms line up, there's a 39-year drought somewhere out there that could potentially occur. And so just some take-home messages now. Drought. The main one is that you see these things like the Millennium Drought, it's the worst on record, or it's unprecedented, and all these sorts of things. Not if you look at the paleo record. Droughts similar to or worse than have occurred before on quite a regular basis in what we know about the paleo, so last 2,000 years. 6 mega droughts in a 300-year period, including a 39-year drought. Also evidence of wet epochs, wetter and longer than anything we've seen in the instrumental record. This one as well I didn't mention, but because this is a drought talk, but there's also work by Ian Goodwin, who's at Macquarie Uni, and he did a reconstruction of East Coast low behaviour based on sand transport off the coast. And what he found was that in the periods where East Coast low activity was greatest, these periods also match up with the periods that the ice cores are saying were, and the other paleo records are saying were really wet. So there's lots and lots of different sources of information. It all seems to be converging on the same finding that this instrumental record is really not enough to give us a proper idea of the true risk of flood and drought in Australia, Eastern Australia. So this has some pretty challenging implications for water engineering, civil engineering. Based on the instrumental record, there's some sort of perception that droughts greater than 5 years long are rare, because we've only had 3 in 100. But if you look at the paleo record, it's not, 5 years is nothing really. If you look at the instrumental record, you would say that a 15-year drought is impossible, but it's not. If you look at the paleo record, a 15-year drought is more than possible. If you're in that century like the 1100s to 1200s, a 15-year drought happened quite often, 3-4 times in a century. We've got this assumption that the flood and drought risk is stationary. We've then got the assumption that if we calculate intensity, frequency, duration curves, and average return intervals, and annual exceedance probabilities based on instrumental record or stochastic modelling, that's going to be sufficient. But the paleo record raises some concerns about that, and if those design metrics are flawed, by default it also means all the infrastructure that's based on those design metrics is questionable as well. So this is just another one, just to finish off, about the yield estimates. So yield estimate is the amount of water that can be produced by a water supply system. So these are based on modelling. You model your rainfall, you put it into a rainfall runoff model, and you put the water into the reservoir, and you calculate how much water can be produced. Now, the process there is similar to what I said before. You take your long record and you account for droughts and so on, and you come up with some statistics about what you think a sustainable level of yield is. And then the idea is to make sure that your demand doesn't exceed your yield. But the problem with that is what this paleo information suggests is that we don't really know what the sustainable level of yield is. The sustainable level of yield calculated based on 100 years of instrumental data might be meaningless if the next 100 years doesn't look like the instrumental period. And so therefore, if we don't really know what the sustainable level of yield is, well then what's the sustainable demand? These are the questions. So some other questions is, we've got the paleo data, and at the very least what the paleo records do is that they give us more examples of those rare but high impact events, the droughts and so on. So as I said before, in the instrumental record we've got just 2 IPO positive phases and just 1 IPO negative phase. Right? And we've got 1 100-year sample. So the sample size is 1. Whereas at the very least what we get by putting the paleo record in is an extended sample size, more examples of extreme droughts and so on, which we're hoping, we're not sure yet, but we're hoping by including that information we get better or more realistic yield estimates. And so that's what we're trying to do. The same applies for climate model projections, and we're working on that as well. So the point is, we don't really know how reliable the existing water supply systems are. And this, I say this not just based on the paleo record. Brendan Berger also did a study on this, based just on the instrumental record and the uncertainties associated with the instrumental record. He said there's about plus or minus 25% uncertainty on the yield estimate. So this was again based on the Newcastle catchment, where the best estimate for sustainable yield was about 60 gigalitres per year, but with a plus or minus 25% uncertainty on it. So it means, you know, anything from 50 to 80 gigalitres is sustainable. Huge uncertainty. And the reason why that uncertainty is there is because that instrumental record is too short to properly constrain the uncertainty. And so if that's what you think the yield estimate is, you're still relying on this next 100 years to be like the last 100 years, which is unlikely. So therefore, what level of demand is sustainable? So that's where we're at. So I'll just revisit that first couple of slides that I set up with that existing approach. Basically, what we're doing is we're hoping what we see in the instrumental record gives us a realistic indication of the true probabilities of drought and flood. So it's hope. What we're trying to do with this new approach is replace hope with statistics based on longer records, based on more samples. Right, so there's definitely still uncertainty, there's definitely still some challenges, but rather than just assuming that the instrumental record is the be-all and end-all, we're trying to supplement that information with some extra information and insights that we're getting from the paleo record. Similar with the climate models. So the climate models just give some more examples of what might be plausible going into the future, and that's also one thing we're looking at. Using the paleo record, again, as I said before, if the next century might not look like the past because of anthropogenic impacts, and so you might say, well, who cares about what happened 1,000 years ago because climate change is happening now, so what happens? But we still need to understand what the baseline risk is before we know what the implications of climate change are going to be, because if you're talking about projections for 2100, you have to apply those changes to something. What we're saying is the paleo information at the very least gives us a more realistic understanding of what the baseline risk is. What is our risk of running out of water right now? What is our best yield estimate right now? We don't really know based on the instrumental record. Hopefully the paleo information gives us a better idea of that. Then when you apply the climate change projections to that re-evaluated baseline risk, that gives you then a more realistic understanding of what's plausible in the future. At the moment, we're applying global climate model scenarios which are highly uncertain to a baseline risk which we know is flawed. So it's a double problem. What we're trying to do is, at the very least, just try to fix that baseline risk estimate, and then hopefully some other smarter people will fix the climate models. I won't say much more about that. So we're trying to fix the short record, and we're trying to explicitly account for multidecadal variability, which is so important for Australia. How are we doing that? This is just a bit of a sales pitch, but there is ongoing work. So we're involved in a big project with a lot of the water authorities, Hunter Water, Water New South Wales, DPI. And the idea of this is, okay, we've got all this science, we've got these paleo reconstructions, we've got this statistics, we've got these re-evaluations of drought risk and flood risk, but what does it mean in practice? How do we actually get that into the water system models? How do we use that to re-evaluate our yield estimates? Do the yield estimates change? If they change, what are the implications for that? Under these different plausible scenarios that the paleo records suggest, what solutions, what adaptation options do we have? You know, there's desal plants, there's bigger dams, there's new dams, there's all these sorts of things. But the costs and benefits of those things have to be evaluated. And to date, they've been evaluated based on yield estimates coming from the instrumental record. If you evaluate the costs and benefits of certain water supply solutions based on what the Palaeoclimate record says, based on the more realistic risk estimates, your cost benefit is going to change a lot. So something which might be seen as not economically viable now, based on an instrumental informed risk, might change if you look at some of the scenarios coming out of the Paleo record. So the other thing that's coming out of this project as well is we've got, I mentioned that tree ring study. So the advantage of tree rings is it gives you a local point, a local source of information in an actual catchment. We don't have any of that for New South Wales. Main reason being because the science of tree rings, the species that exist in this part of the world have been not suitable for tree ring reconstructions. That's changed recently, apparently, according to the tree ring experts. And so they've now identified some trees up in the Barringtons and also some in the Blue Mountains, which have really good potential for being suitable for getting tree ring reconstructions. So part of this project will be coming up with tree ring based reconstructions for the Hunter catchment, so Grahamstown, and also for Warragamba. So that's going to be really interesting, A, just for what those tree ring based reconstructions tell us anyway, but B, it gives us a local point of reference to compare some of the remote proxies like the ice cores and so on. Right? And so where we get agreement, it gives us confidence that what they're saying is useful. Where there's disagreement, we look at why and what's going on there. So that's what we're doing. So in a nutshell, what we're doing is we're trying to go beyond just 1 century, 1 sample of hydroclimatic variability. At the moment, we've got 1 example of hydroclimatic variability and everything's based on that. We're trying to increase the sample sizes by looking at this paleoclimate information. That's it.
Thank you, Anthony and Tess, for really exciting but sobering talk. Any questions from the floor, please? I forgot to mention the organisations you're working for at the moment. So University of Newcastle and Tasmania, but particular, what's the centre that you work for?
Currently, it's called the Antarctica Gateway.
Currently, it may change. Sounds like
Yeah,
okay.
it is changing.
Yeah, okay. And Anthony, the centre.
Centre for Water, Climate and Land.
That makes sense. Yeah. Okay. So yeah, please. Any questions for the speakers? Okay, please.
Has there been any research done into the indigenous oral histories to see whether any of the East Coast nations have any stories that would relate back to confirm any of those ice and treating records that you
I know I think on the Nullarbor there are oral stories about the sea coming in, which would probably be the end of the last ice age. And I think they've tried to sort of roughly date those. I don't know how you would do that to sort of 5,000-6,000 years ago. I don't know if it's just obvious because that's when the sea came in. But for our stuff on the eastern seaboard, no oral histories, but there was one or a couple of studies we found on dust in lakes in New Zealand that were dated back to about that 11th, 12th century period, from a period of aridification basically, and then some hearth sites at campsites that had been abandoned during that period, and then people had come back to them afterwards. So there is, I mean, the dating of those is, I guess, carbon 13 dating sites, like 100 years this way and that way, but they seem to have, those campsites seem to have been abandoned for a period of around 8 or 100 or so years ago. So, yeah.
Anyone else? Please.
Thanks for that. Anthony, is there any guidance of if you're not in a location that has a paleo record or a connection to some long record, if you can assume that your instrumental record has a smaller standard deviation than what's reality, could you say then that, okay, instead of using 1 in 100 year value, maybe 1 in 150 year value, similar to like the climate change kind of guidance, or at least what it used to be? Is there some sort of rule of thumb that could be applied?
Yeah, nothing formal. But
Yeah.
For me, I think my rule of thumb would be based on some of that work that's saying the drought risk is at least 10 times underestimated. So my rule of thumb would be whatever you think it is, times it by 10. That's in the absence of any other information, or at least by 5. I think as a rule, everything is underestimated. Because that short 100 years is just not long enough to pick up the number of events that have happened, and also enough examples of the variability within each of those events. Because the other point about it that I didn't mention is, even though those droughts lasted for 8, 9, 10 years, they were all very, very different in terms of their characteristics, in terms of the time of year, the peak time of rainfall deficit, in terms of their spatial footprint. And so, it's each drought, each flood is very different. And so, to think that we've captured everything that's possible in just 100 years of data is a bit unrealistic. The other point as well is, even though there's no local, you might not have a local proxy in your catchment of interest, there's still these remote proxies. So, for most of East Coast Australia, there's a rainfall, or most of Eastern Australia, but the rainfall is significantly correlated with ENSO. And there's also a strong relationship for most of New South Wales and Queensland with IPO. So wherever you've got a relationship with IPO or ENSO, you can get some paleo information because there's paleo ENSO reconstructions and paleo IPO reconstructions. So at a bare minimum, you could go in and look at what the IPO is saying, and then based on the correlation between instrumental data and the IPO in that instrumental period, you can get some inference about what might have happened in the pre-instrumental period. And that's essentially what we do when there's no local proxies. But then, of course, the local proxies are useful to verify that. But in the absence of anything else, you use the remote proxies. People have used remote proxies for years because the science and the methodology for getting those local has only sort of evolved recently to get it at a higher resolution.
Chris.
Just looking at the graph you showed earlier, which pointed to the available record and indicated periods when we were IPO, we were in some IPO positive, IPO negative. The area that was IPO positive included the period, which is the most recent one in India, from 2010, let's call it, to 2015. That was characterised by some strong, large events, and there's a lot of flood engineers in the room. Yet it didn't make any impact on the IPO, well, very little impact on the IPO. It didn't take it to an IPO negative outcome. What can we take away from that?
This has been a source of discussion between Tessa and I over the last 2-3 days, because Tessa's been up at Newcastle, and we have strong doubts whether we've actually come out of that IPO positive. We think that 2-3 years maybe were just 2 back-to-back La Niñas within an overall IPO positive phase that hasn't really finished yet.
So we might be in one of the 39 years on drought.
So because there is evidence in some of the regional stuff where you go for 10 years of drought, and then there might be 1 or 2 or every 3 or 4 wet years, but then you revert to the overriding drought-dominated state. And so that's one reason. But the other reason is some of the stuff that's going on with the synoptics, and Tessa can explain more about this, but some of the wind patterns and whatnot, it's still stuck in that meridional wind pattern, which is characteristic of an IPO positive phase, not an IPO negative phase. So that's the same work.
Well, that's what I thought was unrelated work to some of the ice core work I'm doing with the new Mount Brown recorders. I have French collaborators, and they've developed an algorithm for atmospheric rivers, which is basically storms that are transporting moisture from low to high latitudes. And what they found is that these landfalling atmospheric rivers around the coast of Antarctica have increased in frequency over the last few years. So that implies that you have to be in a more meridional pattern to get that moisture down there. I mean, a subtropical source of moisture, it's not looking at normal storm tracks, it's looking at the ones that are sending these moisture channels from subtropics to actual snow on the Antarctic continent. So if we were in a IPO negative phase and that made it a more zonal pattern, I'm not quite sure how you get that increase in frequency, unless something really weird is going on in the dynamics of the atmosphere and just change the energy balance between the low and high latitudes so much that these rivers are just so much, the intensity of them is so much bigger. So, that's stuff we've just started working on, but I think it was only when I was talking to Anthony, I thought these things can't get more frequent if we're in a more zonal pattern.
The other point I would say about that as well is, if you remember 98, 99, so there was a really strong 97, 98 El Nino, and then that finished 98, 99, 2000 were quite wet, at least in Newcastle, really wet years. That's smack bang in the middle of that IPO positive phase. So 2-3 wet years, 98, 99, 2000, and then 2000, another 2 or 3, 2010, 2011. But the overall 30-40 year period has been predominantly dry. One or 2 wet years doesn't necessarily snap you out of that. IPO interest. But I mean, the flip side is also that even though an IPO positive is drought dominated, doesn't necessarily mean you can't have a flood. So what it means when it's IPO negative, the flooding is more likely, but the flooding that we're talking about is, the 1950s flood where in Maitland, I think they had 4 1 in 100 year floods in 3 years or something like that. And this sort of, and back to back wet 6 years out of 10 were wetter than average.
Might try and rip through a few extra questions quickly, because I know people will have some early questions. That's cool. So is that covered at least? Yeah. So somebody down here had a question.
I was going to ask if there's any complementary systems happening in the Northern Hemisphere, and if anyone's basically doing your work in the Northern Hemisphere that you can learn from or complement.
Not really. No. I mean, the Northern Hemisphere you need to go to the Canadian high Arctic to get some ice core records. Some of the really big ranges in North America or Greenland. But it's a different system because Antarctica is a continent surrounded by this ocean that does this. It drives such a huge amount of variability. So that reach from between Antarctica and somewhere like Australia is it's readily there. It's just an ocean basin separating them. And the other side of that is that the Danish kind of invented ice core drilling when they took over some of the strange under ice stations that the Americans built during the Cold War and thought, well, let's go ice core drilling. They were all physicists and they were interested in heat time changes and how ice moves and flows over time. So their focus has always been glacial, interglacial dynamics and ice sheet mass balance. How does sea level change due to ice sheets? So I work closely with them. That was their drill in the photo. I have presented this work to the Danish and it's a very green flat country and they just blinked and so no.
Okay, John, please.
Anthony and Tessa, thanks very much for a wonderful talk. The more instrumental data you've got, the happier you seem to feel, and the more you are unlikely to try and give it up. What's the practical way that we can get the most benefit out of that data, and yet move to something that has more of the variability that you're saying that we need to fashion into the data we have?
We're definitely not advocating throw away the instrumental records. There's still a lot of useful information in that instrumental data.
But we kind of think it's gospel, and most people think that that's the best way of forecasting the future. So what are the fundamentals around? Do we modify the data set that we've got to account for what we're talking about, or is there some other mechanism by which we start to move to I won't say rely less on it, but to modify it to suit it?
So I think definitely don't rely on it as gospel. It should be viewed as one plausible realisation of what's possible. That's all it is. It's a snapshot in time that just happens to have been what's happened over the last 100 years. If we took a different snapshot at a different 100 years, you'd have a very different instrumental record. It's just what it is. So don't treat it as gospel. It's just one plausible realisation of what can happen. How can you get the most out of it? I think the stochastic model. You have to use the stochastic modelling because even though it's based fundamentally on the statistics coming out of the instrumental record, at least it allows you to sample more from those extremes. But even when you get those extremes, so the stochastic modelling might tell you what a 1 in 1,000 or 1 in 10,000 year drought is. You still need to go into whatever it is you're doing and within the back of your head saying that more than likely that's an underestimate, or at the very least a misrepresentation of the true risk. It can't be treated as gospel. It's just one example of what's plausible.
What if you split into IPO phases?
Splitting into IPO positive and IPO negative gives you some idea about the upper and lower bound of what might be plausible. But again, there's some limitations with that because you've got 1 IPO negative, 2 IPO positives. So you're still limiting yourself a bit. This is the thing we've been wrestling with for 10 years, and this is why we've got a lot of hope for this paleo stuff, because it gives us more examples of what's plausible.
And then you've got to merge it with GCM outputs and future somehow.
Something like that.
Yeah.
Or ideally the GCMs start to replicate what
which the meetings was. Okay, probably a chance for 2 more questions, so please.
So you comment that the last 100 years are not representative parts of the seems like it's obvious. In relation to the question about the northern hemisphere, supposedly that fact is proven by looking at records from the northern hemisphere anyway. That's a question.
Yeah, there's very comprehensive tree ring records of things like drought, like across North America, the tree ring network they've developed for drought there is incredible. It's maybe one spot for the tree, it's almost like our airway stations or something. And what they've found is a huge amount of variability. They've interestingly found these massive droughts in the 11th and 12th century. So whether that's some kind of subtropical thing that's matched in the northern and southern hemispheres is interesting. But yeah, definitely they've also, their instrumental records are longer, but even then they don't collect the full range of variability.
Who's lucky last? Anybody else? Just one more. Okay, if you can please join me in thanking the two speakers very much.